Okay, here's our video on forces of springs. Forces of springs. Okay, so a spring is, right, anything that usually we think about these as these coiled bits, and maybe you have something attached on one end and then attached on the other end, right? We could stretch this out to have a spring, right, that looks kind of like that. And now we have a stretched out spring. Here is kind of the cool thing with springs. Let's say that this spring is at rest, right? The first one, it's before we've done anything to it. There's nothing is applying a force to it. It's just sitting there. And then the second one, maybe this is, and I'm going to terribly draw a hand. But let's say we have this hand and we are pulling the spring backwards out that way. Okay, the force. Spring force is something that is determined by whatever distance the spring has changed. Whatever distance the spring has changed by, or what we call delta x, right? The change in the spring's position. So this change in that spring's position, this delta x, um, the more we stretch it, right, the harder it is to stretch the spring, the more force we need. What's cool about springs is it actually goes up linearly. So springs will stretch the farther it is. If we stretch the spring twice as far as it was before, then it takes twice as much force. If we stretch the spring 4 times further than we had it stretched before, it takes 4 times the force. So that is what we call a direct relationship, or it's directly proportional. What that looks like is the force of a spring is equal to some constant times x. And x is how much it's been stretched. The constant we will call k. So a k is a spring constant. And this actually is something that you can find on your equation sheet. So if you are to look at your equation sheet, right, there's a thing called simple harmonic motion. This is something that we'll look at more later, but this is just where the expression for the force of a spring can be found. So it's in the bottom middle of our equation sheet. Force of a spring is equal to, and I have on this absolute value of kx. I have the absolute value because a spring could, right, if a spring is here, if that's just at rest, I could also take a spring. I could take my hand and push the spring in, right? I could compress that spring. So if I had my hand pushing the spring in, that would be a compressed spring. And in this case, this would be, right, that's our change in x. That's our change in how long the spring has been compressed. And notice it's not the total length of the spring, it's the change in length of the spring is this x. It is the change in length. The change in its length. Make sure you get that right. The change in its length times some spring constant k. Now, this constant k is something that changes depending on what spring you have. So a different spring will have a different spring constant. So if you ever see one of those springs that's really stiff and is hard to stretch, that means it'll have a really large number for K. If you see a spring that is really easy to stretch, for example, a slinky, slinkies are very easy to stretch out. That means it has a low or a small spring constant. K is going to be a small number. What I mean by that, like a small K, a small spring constant would be somewhere around like 10 or so. And then a large spring constant, large K. Car shocks are a great example of this. So car shocks, if you try to compress a car shock, it some of those have a spring constant around like 800,000 or so, and it can be higher or lower for a car shock. But that would be, for example, a large spring constant K. These will always be positive numbers. But it can range really anywhere. If you get a spring constant in the millions, that's probably not right. If you get a spring constant that's a decimal, also probably not right. Let's take a look at what units K would have. What units would K have? Well, I'll just come over here, right? We have a spring force is equal to Kx. If we look at units now, so units, force is in units of newtons. K is what we're trying to figure out. X is in units of meters. Okay, so what goes in this spot here? Well, we would need there to be newtons on top to match up with the left side. And then to get rid of this meters, we would need to put meters on the bottom. So that's what we see. Spring constant K is in units of newtons per meter. Newtons per meter. Which also means if I were to stretch a spring out by 1 meter, I could measure how many newtons that takes, and that's our spring constant. If I stretch a spring 1 meter, it would take that many newtons to stretch it out by that single meter. So a slinky, right, a small k, that would be 10 newtons per meter. And then a large K, that would be about 800,000 newtons per meter for like a car shock. 800,000 newtons is a lot of newtons. It takes a lot of force to take a car shock, which those normally are around like 2-ish feet long, to stretch that out by an extra 3 feet or an extra 1 meter. Whereas a slinky, it really doesn't take much force. It might, honestly, a slinky might be less than 10. A slinky might be like 3 newtons per meter. Depending on the slinky that you get. So that's units of spring constant. So our equation for the force of a spring, F equals Kx, where K is a spring constant, which is individual for whatever our spring is, and X is the change in length of our spring. Okay, when a spring is at rest, this is something that we call equilibrium. This is just a term for you to know, equilibrium. So up here, right where I'm writing this, is an example of that, right? Where the spring, we're not touching it, we're not putting any forces on it. It's just at equilibrium, it's just sitting there. Okay, so this first question, a spring has a spring constant of 92.0 newtons per meter. Okay, that we just are told the spring constant of 92 newtons per meter. The spring is stretched 2.5 centimeters from equilibrium. What is the force of the spring? Okay, it's stretched 2.5 centimeters. So that means that our change in how long the spring is will be 2.5 centimeters. But in physics, we don't like centimeters, right? We can't have centimeters. We just can't plug it in. We need meters to match up with what's in the spring constant. So 2.5 centimeters, 0.025 meters. You will need to just have this automatic, that transition between centimeters and meters. Practice that. If you have any questions or want some extra practice, definitely reach out and let me know. So 2.5 centimeters turns into 0.025 meters. We're asked, what is the force of the spring? So the force of the spring is equal to Kx. K is, force of a spring is Kx. Right? Always write your equation. The spring constant is 92. X, how much we're stretching this by, 0.025 meters. So the force of our spring, 92 times 0.025, I get 2.3 newtons of force. All right, 2.3 newtons of force. Now that's not a ton of newtons, but we're also only changing the length of the spring by 2.5 centimeters. That's very close to 1 inch. So it makes sense that it wouldn't be too many newtons if we're only changing a spring by 1 inch, especially if our spring constant is less than 100. Less than 100 is something that we could really manipulate with our arms, as opposed to needing like the weight of a car for a car shock, something like that. Okay, next question. A person compresses a spring by 5 centimeters. So compression is over here, right? It's when we go from the spring as it was and then we push it in. So a person compresses a spring by 5 centimeters. Okay, we've changed the length of the spring by 5 centimeters. But remember, we don't like centimeters, so we need to convert that to 0.05 meters. And they are holding with a force of 64 newtons. All right, let's think if we had a spring set up like this. So let's say that's attached to a wall over here, and then this person comes in and is pushing against this, right? Is pushing, and I'll have that's like their hand, their pointer finger, pushing into the spring. Um, okay, so we have this person pushing in with their point. That's just terrible. You can imagine. I'll just draw an arrow, and this is why I'm not an art teacher. Okay, so we've got pushing force. So a force of push, which I tell you is 64 newtons. Let's take a look at the end of the spring, right? A free body diagram for the end of the spring. Okay, well, what's going on with the end of the spring? Um, for most of the right, there's a little bit of gravity down, and if it's sitting on a table, there's a normal force up. But those two forces really don't matter all that much because we're just talking about the spring force, which is acting in that x-axis, right, left to right. So if you want to do the y-axis free body diagram ones to complete it, go for it. I am, in this case, we're interested in the spring force and the pushing force. Okay, so we're pushing this to the left, force of push, and the spring force, right? The spring is trying to push itself back out. So the spring is going to have to exert a force to the right to make that happen. If they're holding, what do we know about those forces? Well, we know that acceleration is 0 meters per second squared if it's holding, which tells us that force of push has to equal the force of the spring. Okay, acceleration is 0, which we could also write as the sum of the forces is 0. That tells us that those two forces have to be equal. So that's how we know that the push force then must be equal to, I'll come back to my red ink for this, the force of the spring must also be equal to 64 newtons. Okay, we're asked what is the spring constant? So spring force is equal to kx. We know the spring force is 64. We are looking for the spring constant. We know x is 0.05 meters. All right, divide both sides by 0.05, and we get 1,280 spring constant units of newtons per meter. All right, and there's our spring constant for this second question here. Okay, moving on. Now we're getting to things hanging from a spring. So vertical springs. All right, so we've got like our ceiling, and then the spring is just hanging down, and we have a box hanging there. We're told this is a 3.2 kilogram box, is at rest, hanging from a spring. Okay, what must the spring force be? All right, well, we have a forces problem, right? It's usually good in a forces problem to start with a free body diagram. So on this box, what forces are acting? I hope you are saying gravity, right? Always good to start with gravity. And then what is holding this box up is the spring force. The spring is holding our box up. Okay, but this box is at rest. If this box is at rest, that tells us that all the forces combined have to be 0, right, for it to be at rest, which also means that then the spring force must be equal to the gravitational force. Okay, so we'll bring this over here. So the force of the spring must be equal to gravity. Since this is something resting on Earth's surface, we can plug in gravity as mg. Okay, so the force of the spring is mg. All right, we'll bring this over here. Force of the spring, mass 3.2 kilograms. G, we know, is always 10 on Earth's surface, which tells us that our spring force must be 32 newtons. Okay, so there's our spring force. If the spring constant, K, is 240 newtons per meter, how much is the spring stretched? Okay, well, we have a force of a spring. We have K. We're looking for the stretch of the spring, right? That's the delta X. That's how much we've changed. we have this equation. Spring force is equal to K times the change in the spring's stretchiness. Okay, we're told that the force is 32 newtons. Or not, we're told, we figured that out in the first one. We are told that the spring constant K is 240 newtons per meter. And then we're trying to find how much has the spring stretched. All right, divide both sides by 240. I get that X is 0.133 meters. And if you feel like it, you could convert this to centimeters, right, by 13.3 centimeters. But I'm totally fine if you leave this in meters always. So X is our change. The stretch of the spring is 0.133 meters. All right, so there's a forces problem involving more than just a spring. Now we're also involving gravity here as well. One more question for you. Getting up to car shocks. Okay, a 2,200 kilogram car sits at rest on 4 wheels. Each wheel is held by the car shock in suspension, and the car shocks each have a spring constant of 180,000 newtons per meter. How much is each spring compressed when the car is stationary? Okay, so we can draw our nice little car here. Right? Car's got to have wheels, otherwise we wouldn't need shocks. Okay, so here's our wheels, and then there's the wheels on the back side. And you got your nice, happy driver who's a safe driver, always follows the speed limits, is very careful and cognizant that coefficient of friction is reduced to almost half on rainy roads and less than a third on snowy roads. Always remember that. You almost half on just rainy, wet roads. Okay, anyway, safe driving lesson over, right? There's a car shock underneath every one of these wheels. And these car shocks, they will compress when the car is set on them, right? We have some weight of the car pushing down. As a reminder, weight, this term, weight, when I say that, I mean force of gravity. When I say weight, I mean force of gravity, or FG. Those are equivalent things. AP will oftentimes use the word weight. They'll also sometimes use the word gravitational force or force of gravity. You never really know, so just know that those two things are equal to each other, that they mean the same thing. Okay, anyway, looking at this car, let's draw a free body diagram for it, right? We've got a forces problem. It's good to have a free body diagram. My question, though, is how do we know this is a forces problem? Well, forces is the only way we've learned how to deal with spring constants so far. So right now, when you see spring constants, that's the only thing that it could possibly be. All right, so on this car, right, we have force of gravity down. And then what is happening on this car? What 4 things are keeping it up? Well, it's these 4 shocks, all 4 of these. So we've got 1, 2, 3, 4. So force of a spring, force of a spring, force of a spring, force of a spring. If we're told, though, that all 4 of those forces are from spring constants or springs that have identical spring constants, then we can just say each one of those forces of spring are equal to each other because they're all going to be the same spring force. Okay. Let's then, right, free body diagram. So good. Next place to go, sum of the forces is mass times acceleration. We only have forces in the y-axis, so that's what we'll look at here. We have 4 spring forces up and a single gravitational force down. What do we know about our acceleration in the y-axis? Well, the car's not jumping up and off the road, not sinking into the ground either, so that'll be 0. So we can say that 0 is equal to 4 of these spring forces minus force of gravity. Tells us that force of gravity is equal to 4 of the spring forces. Okay, let's plug in, though, for each of these, because we're not asked about force of gravity. We're not asked about spring forces. We're asked how much is each spring compressed. That's what we're looking for. So we're looking for what's that X? Okay, so spring force, as we've learned, spring force, it could be replaced with kx. Gravitational force, as I'm hoping is automatic for you, is mg, because this is on the surface of the Earth. All right, now we have numbers we can plug in. Okay, mass, 2,200 kilogram car. G is 10. 4, our spring constants here, 180,000 newtons. And then our change in length, or the compression distance, is what we're looking for. Okay, so plugging this in, 22,000 is equal to, let's see, 4 times 180,000 would give us 720,000 times that change in length. Divide both sides by 720,000. I get that x would equal 0.0306 meters. So that is a compression of, if you want to put this in centimeter terms, 3.06 centimeters. Again, you don't have to put it in centimeter terms. I just know that you all probably know what a centimeter is, as opposed to knowing what 0.03 of a meter is. So just by your car sitting on top of the shocks, they are being compressed by about 3 centimeters, or a little over an inch, just because your car sits there. Now, obviously, that would change from car to car depending on the mass of the car or the spring constants of your shocks. But that would be for this problem. All right, and that is it for this video. If you have any questions, definitely let me know. Otherwise, we'll see you next time.